topic is the cylindrical shell method for finding volumes of revolution. Um, in the previous video, we learned about a method of finding volumes of revolution called the disk washer method, where we were stacking up either circular disks or disks with a hole in them that we called washers. Um, so, in the case of the cylindrical shell method, what we're doing is we're going to divide up the solid a little bit differently. And because we're still just dividing it into different, into different little pieces, we're going to add them up and still get the same sort of volume. But the pieces are going to have a different shape, and those shapes are going to look like cylinders. So let's suppose that we want to find the volume of the solid obtained by revolving the region below the curve y equals x squared plus 1 on the interval 0, 2 about the y-axis. So I'm revolving it around the y-axis. Now, so here's what I want to do. What I want to do is add up shapes that look sort of like this. Let me just draw a particular cylinder. So I'm going to draw a cylinder that looks like this. Let's draw in the front of the cylinder too, just so we can see that it looks like a cylinder. Hopefully the perspective on that is right. So what I have here is I have kind of I have a cylinder that is this tall, and it has a circumference on the top that looks like that. So the question is how we can use this to find a volume. Well, the answer is that we're not really using just the cylinder. The cylinder itself, I know many people think of it as like the can and its inside, but really a cylinder just refers to the surface of a can, not the inside of the can. The surface, of course, as we know, is like an infinitely thin piece of paper. It has no volume at all. What we can do is we can give this cylinder a little tiny bit of thickness in like that. So it's not really a cylinder, but rather a cylindrical shell that has a little bit of thickness. Now, I bet you can guess what we call this little bit of thickness, because this is calculus. We call it dx. That's generally what we call any tiny bit of distance in the horizontal direction. So let's take a look at the dimensions of this cylinder. The height of the cylinder, let's see what color I should do that in. The height of this cylinder, like that, is just going to be the height of this function. Remember, this point here is x squared plus 1. So this height is going to be x squared plus 1. Now, what's the circumference of the cylinder like that? I'm only showing really half the circumference on the top, but if you follow it all the way around here, you get the whole circumference. Well, we know the circumference of a circle is given by the equation c equals 2 pi r. Well, here's the center of that circle, and here's its radius. So we're going to pick some arbitrary point. Remember, we've already decided the x value that belongs to this point is x. So that means that this distance here, the distance from the axis of revolution to the outside of the cylinder, is x. So that means that this circumference is going to be c equals 2 pi x. Now, let's see what happens when we actually unroll this cylinder. I'm going to go down here for a minute. Don't worry, I'll come back. If I unroll that cylinder, let's kind of draw it like this. Let's see. There we go. So the reason I'm doing this is I'm trying to make it look more like a rectangular box. So this is going to be the thickness dx right there. And the curved surface that I've drawn as the curve, this is going to be the side that has 2 pi x. And let me actually put these in different colors. So that's going to be this side here. That's the red side. And let me use blue for that side. So that's going to be that side, and that's going to have the dimension x squared plus 1. So what I really have here, if you look at it, maybe if I draw it a little bit more like this, is I actually just have a very, very short box whose dimensions are dx in the height direction, x squared plus 1, and 2 pi x. So it's fairly easy to see that the volume, let's write this down here, the volume of one cylindrical shell is just length times width times height. So that's going to be 2 pi x times x squared plus 1 times dx. Where if I had to label these, I would say that this is circumference, or width, of the width when I roll it out. This is the height, and this is the thickness. You can label them anything you want. The point is that I have a product of lengths in 3 different dimensions, so of course that's going to give me the volume. Well, if we have the volume of one shell, let's see what happens if instead we have all the shells. So let me just draw in here another shell like that. And that shell, of course, it has a different radius and it has a different height, but I can still define them in the same way. Its radius is still going to be a distance of x from the axis of revolution, and its height is still going to be x squared plus 1. It's just that we're at a different point x, so the value of x is going to be different, but the equation doesn't change. So what I can do is, if this is the equation for the volume of one shell, guess what I can do? I can add up all the shells using the magic of the integral sign that looks like an S for sum, and I simply do that from the lowest possible value of x, which is 0, to the highest possible value of x, which is 2, and this is now the volume of the full solid of revolution. And that's the method of cylindrical shells. Now, there's sort of a very simple version of this formula that exists if certain conditions are met. In other words, if f of x is greater than or equal to 0, and the region is the region under y equals f of x. In other words, we're looking at a region, as you see in this curve, where we have a positive curve and we're looking at the region between that curve and the x-axis, and the axis of revolution is the y-axis. Then we can think of the volume as equal to 2 pi integral from a to b of f of x dx. In this very, very specific circumstance, this formula gives you the volume of revolution by the shell method. And by the way, all I've done here, the reason this 2 pi is sitting out here is that that's just a constant, so I just moved it out there like that. So, and that's usually how you'll see the formula written. Now, as you can probably guess from the fact that I'm saying that this is a very, very simple version of the formula, obviously we're going to be doing examples where the region is not simply defined as being underneath a wholly positive curve, and where we're not using the we're not using the y-axis as the axis of revolution. You're going to have to understand the geometry, but perhaps a more general way of understanding this formula is that the volume is equal to 2 pi times the integral from a to b of the function that gives the radius times the function that gives the height times dx. You can think of it that way. And you might guess, is there a way to do this in the y direction where even that generalization doesn't apply? Sure there is. So we'll get to that. The point of this exercise, by the way, is really to be able to set up the integral, but we can in fact find the volume, and I know some of you are not going to feel resolved unless we actually find the volume. So let me just quickly evaluate the integral. I'll just zip through the algebra. So there we go. The volume of the solid that I've described up there actually is 12 pi. I don't know if you find that more satisfying than just setting up the integral. I know that you know how to find antiderivatives and how to evaluate integrals. The much more interesting problem is to be able to set up the integral from the geometry. So in the interest of saving time, that's what we're going to be doing for the rest of this video.